Okay. Hello. Okay. Hi. It's been years since I've done any stream, so I'm not very sure if I'm live right now. I've clicked the go live button, but I have to check. Or if somebody can tell me in the chat if I'm live. I forgot how to check the chat. Wow. Okay. Yeah. See. Just give me a minute. Okay. I think it should be working. Back from dead. Why back in CP? By the way, I think there's a 5 second lag. I tried to measure it. It's like a 5 second lag between the chat and like what I'm saying. So if you're writing any message, like you should expect a response after like 5 seconds. Yeah. Oh, somebody in the chat is saying I forgot my password for like 3 4 years. Nothing. Right. Why have I been gone for so many years? Yeah. So I've been really busy with work. I know it sounds like an excuse, but that's true. I'm still busy, but like now I'm thinking like I really like this part of my life, so I should really make time for this, even if it's a little hard. I should really try. So that's that. Wow, we don't have a lot of viewers, but I think that's a good thing because it's been so long. I'm not very sure I'll be able to do a good job. But yeah, uh, so before we start, I just want to ask if the audio is fine, if the video is fine, is everything fine? Wow, he's alive. Wow. So I just wanted to ask if everything is fine before we actually start. Gotta wait. Yeah, everything is fine. Okay. Yeah, thanks. Okay. So yeah, so I did this contest after a long time, I guess. And the stream is like, if you see, my previous stream was like 4 years ago, and then the current stream is like a moment ago. Have you left job? No, no, no. I'm still doing my job, but like, uh, I don't know how I'm gonna manage this, but I'll try really hard to, be regular on YouTube now. So let's see. Anyway, so yeah, so my previous stream was like 4 years ago, and now we're gonna do this again. So anyway, yeah, I'm surprised I still have old viewers because didn't you all graduate? Like, why are you still here? So anyway, is the WLB that bad at Graviton? It's not about the work-life balance. It's like you have to do your job, then you also have to socialize. You have to do other hobbies. I guess it's not about the job. It's more about adulting. You have a lot of stuff to do when you're an adult, and that's what I am. So anyway, so this contest, I'm not even sure after how long I'm doing a contest. Uh, I think my previous one. Okay, sorry. My previous one was like okay, not that long ago, maybe 4 5 months ago. I did a contest, Div 4. But yeah, so it's been a long time, and I managed to solve like 5 of these problems today. Okay. Oh wow, you saw my channel before joining college. That's great. Nice, nice. So anyway, so is there anyone who's actually here for actually the problem discussions, or only old people reminiscing? Did you guys do this contest? Yeah, okay, great. Okay, so here for both. Wow, solved 4, nice. Yeah, so people who are watching, like, can you just put it in the chat how many problems you were able to solve? Love you, Shivam. Anyway, yeah, so let's start with the problem. So uh, let me also open my submissions. Right, so I was able to do this in like 1 minute and few seconds, I guess. Oh, I'm the only friend who did this contest. Wow. So all my actual friends who used to do competitive programming, they all graduated and retired by now, and I'm the only one who's still doing it. That's funny. uh, AI cheaters. Wow, yeah, so I haven't tried using AI for competitive programming, but I have been using Copilot for my job, and yeah, that's really helpful. I mean, can't do stuff on its own, but like it really, like it's very good at the autocomplete stuff. Like if I have to write three similar lines, after writing the first line, it automatically suggests me the other two. So that's a very good thing. So I'm not sure how much Copilot would help with this competitive programming. I haven't tried ChatGPT either, to be honest, and I really don't have ChatGPT Pro. But I've been seeing some posts on LinkedIn that it's really good. Claude 3.7 is just game over. I think in the future maybe I'll do a video and I'll see how good these LLMs are at competitive programming. But yeah, even if here's what I'll say. Even if LLMs can do competitive programming and they are very good, I think it shouldn't matter, right? So, for example, chess engines are like very good, okay, and there's no human who can defeat chess engines like I think Stockfish. Yeah, so there's no human that can defeat Stockfish right now, but that does not mean you stop playing chess, right? So you can, like, the aim of competitive programming is to. Bobby Fischer had a TED talk about this. Yeah, I mean, I haven't heard that, but I guess that's the point. But yeah, anyway. So what I'm saying is, just because computers can do better than you, and that's not true, by the way. Humans are still better than LLMs. Even like at least right now, they are better than humans. I'm not sure about maybe 2 years down the line. But yeah, even if LLMs are better than you at this, it doesn't mean um, competitive programming is useless, right? So it does still help you learn programming, and even if you want to go towards AI research, some of these skills will transfer there as well. So yeah, people keep crying about AI, but it is fine anyway. So I think we are increasing some. Yeah, please start solving. Yeah, okay, so this is the first problem, Cloudberry jam. And okay, so this is a very simple problem. I don't know why they tried to confuse us with the story. It took me, okay, 1 minute and few seconds, I'm not sure, but yeah. So like the most valuable berry something something, usually I'd skip this story. It's just asking how many kilograms of cloudberries are needed to prepare n 3 kilogram jars. Okay, so I guess we should read this previous paragraph. So like to make jam, you take equal amounts of berries and sugar and cook them. So if you have 2 kilograms of berries, you need 2 kg of sugar, and then with this entire four, you just get 3 kg of jam, right? So long story short, this is some useless information. 25% evaporates and so on. In the end, it's just that when you take 2 kgs of berry, you get 3 kgs of jam, and they're asking you how many kgs of berry is required to make n 3 kilogram jars. So for one 3 kilogram jars, you need 2 kgs of berry. So for n, you need 2n. So basically, that's the solution to this problem. You take n as input and you output 2n. So you can see here, for 1 there's 2, for 3 there's 6, and that's exactly what I've done here. If you see my solution, so this is my template. I think anybody who has been into competitive programming for some time would definitely understand what templates are. But yeah, anyway, so this is also the part of template. But anyway, I take the number of test cases, I input it, and for every test case, I call the solve function. And inside that, I'm just taking n as input, and printing 2n as output, and that's it. That works. You can see the test details for all the tests. It's just for 1, 2, 3, 4, 5, 6. The output has to be 2, 4, 6, 8, and so on. Yeah, this one was easy. They tried to confuse us with the story, but like uh, you know, that's not that confusing. Yeah. Second problem made me cry. Oh, Let's see. I actually forgot what the second problem was. Let me see that again. Okay. Oh wow. Oh wow. Yeah. So I do agree. It's a little bit hard for a Codeforces div to be, because there are some corner cases and there's a chance you might miss some of those. Luckily, I got it right on the first attempt, and actually, Actually, I think I did make some mistake on my local testing, but like I was able to get it in the first or second attempt. But yeah. So anyway, so this one, let me pull out my whiteboard or blackboard, something. Yeah. Anyway, so, okay. So there's an array consisting of n positive and solved it in 1 minute faster than you. Yeah, I mean, I've become very slow at reading these problems now because it's been 3 years since, you know, like there's some intuition involved in reading these problems. Like, there are a lot of sentences written, and when you're regularly doing competitive programming, you know exactly which sentences you're supposed to read. Like, sometimes there is a lot of useless stuff in these problem statements, and you have to quickly filter which part is relevant, and like some people are really good at it, right? So I'm not anymore, but yeah, once I understand the problem, I'm still, I guess, fast. But anyway, so yeah, pre plus suff plus bs. Pre plus suff plus bs, I think that's not what I did. I think what you're saying is prefix sum plus suffix sum plus binary search. No, that's not what I did. For every L we choose R. Yeah, exactly. Anyway, so I think none of those things are required. Suffix sum, prefix sum, I think even binary search, none of that is required, right? So at least in my solution, I haven't done any of that. Uh, oh, hi, wannabe 21. Okay. So anyway, so in this problem, we're given an array of n positive integers and also an integer k, positive integer k. So we have to create an array b with these rules that it contains n into k elements, and then the first n elements are the same, and then for any I greater than n, this thing holds, right? So once you try to understand what actually happening, and you can even use this example to understand what's happening. It's just that you have an array A and you have to make k duplicates of that array and then concatenate them. So for example, if your array was something like maybe 2 4 1 3, I think I took the exact I think I took a similar example. And then if k equal to 3, what you have to do is you have to just put 3 copies of this. Okay, so yeah, so that's what you kind of have to do to make the array b. So this is your b. Just just have to make some copies of the original array. Now you're given a number x and it is required to count such positions L with for which there exists a position R such that R greater than L. It sounds a lot like that epsilon delta kind of thing, right? For every epsilon there's a delta such that blah blah blah. So I think it confuses some people, but here it's not that hard. So what they're saying is for every L there should exist a segment such that that segment starts at L and ends anywhere, and then the sum of the elements inside this segment should be at least X, right? So for example, let's say if this is the L, you have to pick some R, you can pick any R, and then the sum of all the elements in this range has to be at least X, and X is also given to us in the input, right? So the first thing that I noticed here, and the first thing that you should have checked here as well, is that all the elements in the array A are positive, right? So had they been negative, it would have been a much harder problem. I don't know how we would have solved it. I'm not even sure if it can be solved for the given constraints. But yeah, but like since all the elements are positive, we know for sure that if basically if this R works, then this R will definitely work, because the sum of the range that we're talking about will increase as we increase the range. So basically for every L, we will just pick this as the R, and we'll just check if the sum for this, for this suffix is, greater or equal to X, right? So yeah, so some people are saying in the chat, I tried to loop from the last element in the array B and so on, right? So the problem here is that the size of the array B is n into k, and both n or k are up to 10 to the power 5, and if you multiply n and k, then that's around 10 to the power 10, and yeah, so 10 to the power 10 is too large, and if you try to make an array of that size, or if you try to even do that many iterations, it will give you memory limit or time limit, right? So if your solution is O of n into k, then this fails, right? So O of nk wouldn't work. So you have to do something like O of n plus k or something like that, right? Switch ki tayari, wow. I mean, I can do that quietly, right? So I don't have to stream it. Anyway, my HR can watch it too. Anyway, so yeah, so what I was saying is, you can't actually make the array B because basically the number of elements in the array B is too high, and you just can't make it. So the array B, you have to kind of make it virtually. Like you have to work with it without actually making it. So anyway, what I will do here is that right, so basically we just have to see the first element from the right, such that if you take the suffix sum from here, it is greater or equal to X, because if this element works, then all of these will definitely work, because uh, all of these will definitely work because, like, when you decrease the L, then it increases the size of the range, and when the size of the range increases, it means that the sum will definitely increase. So what I'm saying is, if the sum of these elements is at least 10, then obviously the sum of these elements will be 10, the sum of these elements will be 10, and so on. So all you got to do is you have to find this element, right? So you have to find the first element from the right, such that the suffix sum of that from that element is greater or equal to X, right? So yeah, but we have to do this without actually making this array. So one thing that can help us is that this array is simply k copies of the original array A. Okay, so now there are a few cases here. So one case is that, what if the sum of this entire thing is greater than, what if the sum of this entire thing is smaller than X, right? So if the total sum is smaller than X, then there is no way you can pick a suffix from this such that its sum is greater than X, right? So if total sum, basically if the total sum is smaller than X, then basically you have no answer. No answer, or basically I think you'll print 0 here, right? So then answer equal to 0, right? If the summation of all the elements in B is smaller than X, you can do that. How will you take the summation of all the elements in B? It is nothing but equal to k times summation of A, right? Because this is just k copies of A, so you just take the sum of A and then multiply it by k, right? Can we use binary search? Now that I think about it, yeah, maybe you can use binary search. You can binary search to get the index of L, and yeah, you just have to quickly find out whatever the sum is. But yeah, anyway, I didn't do any of that. So what I understood was that, so this was one of the corner cases. Let's say once we're done with that, what I understood was that our required element will be in one of these boxes. Either, like, if we have 3 of these boxes, it has to be inside one of them. So let's say it's in this one. So this means that the sum of this box has to be smaller than X, right? So till the sum of this box is smaller than X, we keep on subtracting this from X, and we can keep on counting how many of these boxes we've subtracted. So my code is a little ugly here. I'm not very happy with how I've implemented this. But yeah, so first I have n, k, and x. I take a as input. This is some macro. But yeah, anyway. So after taking the inputs, I have sum equal to 0. I take the sum of the array A. Okay, and then this is the corner case. If sum times k is smaller than x, then the answer is just 0. Because like if you have the entire array and yeah, if you have the entire array and you're still not able to kind of get the sum to be equal to x, then there's no way you can do it, right? But then you get to this part where the okay, so I have a variable called count, and count is the number of boxes that you can sort of take completely. So like for example, if the answer is inside this box, so then the count has to be 2, right? Because this is the number of boxes that you can completely take, and that has to be x divided by sum. So why is it x divided by sum? Because what we're doing is we're subtracting these boxes one by one till x is greater or equal to the sum of this box. So that will just be x by sum. Basically, how many times you can subtract sum from x such that x is still greater or equal to 0. So yeah, after that I have a variable called c2. It's like a second count. So that is just you iterating on this second box. So like you have to iterate on the second box. How many elements can how many elements do you need to subtract from this to make this x at least 0, right? Basically let's take an example that will be better. So for example, if my value was 24, right? So if x equal to 24, then basically and the sum is equal to 10. So the sum equals 10, and then count will be x by sum equal to 24 by 10 equal to 2, right? So that means we can take 2 of these boxes completely, and then we need to take some of these elements as well, right? So it turns out we have to take these 2 elements, and we have to iterate from right to left here. So you can see I'm sort of doing the same thing, iterating from right to left, basically counting how many elements can I take from there. And so this is some sort of n minus 1 minus I means that I'm taking it from the right side. But yeah, so C2 is sort of how many elements can I take from the right, and so this is total n into k elements are there, and we subtract n times count from that. So if you had if you were here, you had to subtract basically n times count, as in 4 times 2. So 8 of these elements you can't take. So I'm saying out of these 4 times 3, 12 elements, you can't take 8 of these, or you can't take 2 into 4 of these, because if you start here, you will not be able to get the sum greater or equal to x. And then you also can't take C2 of these elements, right? So minus whatever, maybe this will be 1, because I started it from minus 1. So yeah, so you can't take these many elements. So this is like the total is 3. So if you start in any one of these 3 places, you can sort of satisfy the condition, otherwise you can't. So yeah, but for L it would be ideal to choose R as the last element, that is the n times kth element, right? Yeah, for every L you have to choose R as the last element. We can also do it like much shorter implementation, suffix sum plus alpha into total sum, find this minimum, and yeah, range will be. So what you're doing with suffix sum, I'm doing that here, like the same thing. I'm doing it like both will take linear time. I think to some people what would be easier is binary search. So binary search might be easier for some people. So let's say you want to binary search for the I will discuss the binary search solution also. So like you just have to binary search the smallest L for which the condition satisfies. So you just have to do basically you just need the sum in this range and check if it is greater or equal to 24 or not. And to get the sum in any range, for example this range, you just have to check how many boxes are we taking completely and how many more elements are present here. For that maybe you can use suffix sum or something. Maybe you can even iterate linearly and calculate what the sum is and so on, right? So this should be easy. You didn't implement binary search because the other one is more intuitive. Yeah, exactly. The other one also seemed more intuitive to me. I just have to find kind of the last element which works, and you can just iterate from the right side. That makes more sense. Yeah. Okay, so now these were like the okayish problems. Now let's start with the more interesting ones. Okay, so how many of you tried C but were not able to solve it, and how many of you were able to solve it, right? And how many of you didn't try it? Just writing me wouldn't help because solved, didn't solve, tried, no, not solved, nice, not able to solve. Okay, anyway, so yeah, so C is good. Um, to me, it was a bit standard, and that's why I kind of fucked up on this one because yeah, I'll tell you. So anyway, uh, so what I fucked up was when I read this that the answer for each query is calculated independently. I thought we just have to erase one element in each of the basically each of the answers. We have to erase just one of the elements. That's what I thought, but that's not true. But yeah, let's read the problem first. So they define what a permutation is, and then yeah, so in each query they will yeah, hi Kaushik. So in each query you zero one of the elements of the permutation. So basically you're given a permutation and you're given some queries, and all of these are distinct. Basically this is also a permutation, but yeah, in each query you take some element from this permutation and you change that with a zero. And then after each query you have to find the minimum number of operations required to fix the array. And by fix you mean you have to make it a permutation again, any permutation. And to fix you can perform these operations. You can choose an integer and replace the ith element with I. Okay, so basically my intuition says that there will be zero present somewhere, and since zero is not a part of the permutation, I have to replace that with I. And yeah, so that's how it will begin, and then let's see what will happen. So as you can see, you really should have seen this note here, because yeah, so here it tells you that in the first query there's 1 0, then there are 2 zeros, then there are 3 zeros, and there are 4 zeros, and so on. I got a little confused. I thought you know, like in each query there's only 1 0. I thought in the first query this will be 0, and then in this second query this will be 0, and this value will come back. So that was wrong, and it took me some extra time for this one. Let's see how much it took. Yeah, 20 minutes. I think 12 minutes. So I could have done maybe a little more faster, but I got stuck here. But yeah, anyway, so this is the case. One by one the elements will keep on erasing. So in that case it would have been a much easier problem. Not really. So there are two different solutions here. For one, the solution which I did in that case, this is an easier problem, but there's also another solution in which this is the easier one, right? So I'll tell the other solution first. So anyway, so it's a very standard approach. It's a very standard technique in which you sort of make cycles from a permutation, right? So if you have a permutation of 5 elements, and the elements are like maybe 3, 1, 2, 5, 4. Okay, so you can and if you write the indices here like 1, 2, 3, 4, 5, and then you sort of connect these two. No, you're wrong here. But yeah, anyway, so if you sort of connect these two, and I was saying to the chat anyway. So yeah, if you connect these two and then you connect these two and then you connect these two, so it forms a sort of cycle. So like in this one you can see if I connect 3 with 1 and then 1 with 2 and then 2 with 3, right? So it makes a cycle, and then this creates another cycle. Like you can make one more cycle, like 5 with 4 and then 4 with 5. So yeah, so that's another cycle. After so many years, what's the reason? Yeah, because why not? So this was a graph problem. Yeah, kind of. This was kind of a graph problem. You can also do it with disjoint set union. There might be some other ways as well. But yeah, so very standard thing is to sort of make cycles from a permutation, right? Like you can technically solve it without knowing graphs. Okay, so I will also tell you the intuition behind this, like why are we making the cycles here, right? So anyway, if you go back and basically right, so let's say if I erase this and then I put a 0 here. Okay, so what will happen? How will we solve this? Basically we have to put I here, right? So we have to use the operation here. We have to remove this 0 and put 3 here. But what about this 3? So now you have a duplicate, and that does not work, right? Because you can't have duplicates in a permutation. So what you will do is you will remove this 3 as well, and you will put a 1 here. But then what about this 1? Because again you have duplicates, so you have to remove this and put a 2 here. And since 2 is already here, so this works, right? So you can see that these two were not affected and these were affected. So if you kind of trace this, you'll see that it is a sort of cycle. So like you start with 3, and from 3 you go here, and from here you go here and here and here and here, and then back to here, right? So you can make the cycles from the beginning itself. So 3 is connected to 2, and then 2 is connected to 1, and 1 is connected to 3. And basically if any of these elements, if you remove them and put a 0 there, you have to sort of um, apply the operation on all of these. So like if I if I remove this and put a 0 here, then again I have to remove this and put a 1 here, then remove it, put a 2 here, remove this and put a 3 here, right? So yeah, you have to divide it you have to divide it into components, right? And basically that's sort of what you have to do. Okay, and basically in any cycle or in any connected component, if there's at least 1 0, then you have to apply the operation on all of the elements of that connected component. And then if there is another component, if that becomes 0, then you have to apply the operation on all the elements of that connected component as well, right? So you can do it with DSU, you can do it with simple I think you can do it with simple DFS also, like not DFS, like you can do it very simply, like whenever there is a 0 anywhere, just start I'll call it a DFS, but you don't need to know what's a graph to do this. Just remove this 0, put a 1 here, and then find where's the 1, then put a 2 here, and then find where's the 2, just put the 3 here, and like you're done. So do this, count how many changes you've done, and yeah, so you can do it without DFS. What I did was I sort of made these sets using a technique called disjoint set union. Some of you might be knowing that. So with that you can easily get the size of any connected component. You can join the connected components and so on. So like that's easy. Yeah. So this is my solution. Cycle size, exactly. So yeah, basically this is the, I think this is the DSU part, disjoint set union or union find data structure. I think, I don't know, union find disjoint sets, UFDS. Wouldn't the time complexity of brute force be n square? Not if you mark the elements visited. So like basically, if you iterate this connected component and you sort of mark all of these visited. So next time, like if you put a 0 here, when you put a 0 here, since all three of these are already visited, you won't go over it again and it won't be n square. Yeah. So anyway, what I did was union find. So I have this find set and union nodes, very standard functions. With this, you can kind of get the parent of any set, and with this, you can join two sets. And these are some helper arrays and initializations. But yeah, anyway, so you take the inputs, you join I and pi. So for example, you just join 1 and 3, sort of like adding an edge between them. And yeah, so every time you find a set, basically find set is finding the parent of that set. So for every query you find that set, you put that into another std set, and if it is not there already, you add the number of elements in that to your answer and you print your answer every time. So mostly that's it. That's all you have to do. The DFS solution is, I think, actually easier than this, because you kind of don't have to keep track of. So yeah, so you kind of don't have to keep track of how many sets have been done. You just have to mark all the elements visited, and that's it. Uh, so yeah, should we move to the next problem now? For any doubts? This one was good. So yeah, this one was good. So how many people tried, again, tried, solved, not solved? Problem D. D and E were both very good here. E was very, very nice. E was a very nice problem. Yeah. Oh, solved D. Nice. Okay, so the statement is pretty simple. It's a combinatorial problem. Like you have to count the number of strings that kind of satisfy this. Right. So you have a pair of indices I and j such that yeah, for every pair of indices I and j, if the letters at those positions are equal, then basically I minus j mod 2 has to be 0. 0, 1 knapsack, sort of, followed by some extra combinatorics, right? Combinatorics. Yeah, I hope I'm pronouncing it right. But yeah, anyway, so what you understand from this is that basically the same character has to be either all, like if you have 4 A's, then either all A's are at even positions or all A's are at odd positions, right? So you have to divide your string into like 2 buckets, sort of. So let's say this is your string, right? So what you have to do is you have to make one bucket from all the odd indices and then one bucket from all the even indices, right? And then let's make these blue. Yeah, sort of, that's what you have to do. And after that you have to rearrange them as well. Like for example, uh, if you have 2a and 2c, and let's say you put AACC, or maybe you can do ACAC, or you can do ACCA and so on, right? So basically, let's say These are the even indices because it starts from 0, right? So let's say we have E even positions and O odd positions. E even positions and O odd positions, right? So basically what you have to do is first you have to partition your characters into uh, even and odd. Like you have to either put all into the even or you have to put all into the odd. Any character, like if you have D, you have to put either all D into the even, let's call it NE and NO, right? So you have to put either all D in the even bucket or in the odd bucket, and after that you have to sort of make permutations inside the bucket as well. So for example, the same thing that I'm saying, AACC, ACAC, and so on. So how many ways are there to do it? It will be something like NE factorial divided by 2 factorial multiplied by 2 factorial, right? So basically it will become your number of even divided by whatever characters you put in the even bucket. So it could be like, let's say, I'll call it count of A, count A factorial and count C factorial, right? And then all the other characters, let's say they are in the odd bucket. So you're like NO factorial divided by count of B factorial, count of D factorial, and so on, right? So basically what you have to do is you have to partition them into two different buckets, even and odd. And then after that you have to multiply NE factorial, NO factorial, and then divide that by count of A factorial, count of B factorial, and so on. Like, so it has to be, so like in the denominator, all of the terms will be present. Count A, count B, count C, count D, everything will be present. Is the stream buffering, by the way? I can see some buffering. If 29 drop frames. Is it buffering? I'm not very sure. I'll try to, manage next time. But anyway, everything is fine. Yeah, great. So yeah, the answer is just, this thing you have to multiply. You have to multiply this thing at the end. But before that, you have to find the number of ways in which you can sort of put like all the A's into either even or odd and so on. So if you think about it, it's sort of like DP, because coming back to this problem, it's like, how many A's are there, how many B's are there, how many C's are there, and so on. And you kind of have to, either put all A's in the even bucket or the odd bucket, and then kind of uh, like the total number of events has to be a certain value, right? So I think I'll be able to explain it better with the code. Right, so first I take the input, then I take the total sum, and I take the factorials till that sum, because we will need the factorials someday. But yeah, and then at the end I multiplied it by factorial of E and then factorial of O, and also this answer divided by factorial of count of all the characters. So this is just this part, and then followed by this part, right? My PW function will give multiplicative inverse using Fermat's little theorem. Oh, hi Ashutosh. Don't you use modular integer template? I'm not using any templates at all. That was all in my old laptop, and then I don't have it anymore. You can see in the previous problem I even wrote disjoint set union from scratch. So you can see in the previous problem I wrote DSU from scratch, so I don't have any templates. I was really scared if some segment tree problem comes, because I'll have to write segment tree from scratch. So since a long time I've been writing everything from scratch. It's not that fun. It is a little fun though. Anyway, so yeah, so now this is the DP part. DP is just basically till which character you reached, and how many uh, events, like how many total characters are in the event bucket, right? So this is the DP. Just give me a second. Yeah, your DPIJ is simply uh, processed first I characters, processed first I characters, and this is from 0 till 26, 0 till 25 actually. And then J is and total J are present in event bucket. Any idea why I didn't also why I don't take DPIJK, and like I also take how many are present in the odd bucket? Because we don't have to, because NE plus NO is always equal to total, and since this is constant, so you don't have to keep both, because you can get NO as a function of NE, right? So because of that, you just have to take J, you never have to take K. So yeah, that's why this works. Anyway, so yeah, now the transitions are pretty simple. This is the initial condition. Basically, uh, these are the two conditions. You can, either take the first character, that is A, in the even bucket or odd bucket. So there's one way of doing both of those, and then for the rest of the characters, you iterate on the arrays, and then there are two ways to do it. You can either not take or you can take. So not take is pretty simple, just copy it from the previous layer, and take. And for the take case, you have to make sure that CI is at least 1. So like basically, if CI is 0, then take and not take are the same thing, right? So CI has to be at least 1, and your J is greater or equal to CI. That's because you're doing J minus CI, like that's the element you're copying from the previous layer. You can also think, yeah, yeah, exactly. So you can also think of it like, yeah, so you can also think of it like, we want to get 10 elements in the, let's say J is equal to 10, so we want to get 10 elements in this current bucket. So um, in the even bucket, if we want 10 elements, and where and the current character is having frequency more than 10, it has 15, so obviously you can't put it in the current bucket, because then it would be impossible. So yeah, your answer is DP of 25 comma E. So E is basically how many events you have. O is how many odd you have. These are actually interchangeable. You can check DP of 25 comma E will always be equal to DP of 25 comma O, because basically filling the event bucket is same as filling the odd bucket, because basically every take is not take for the other bucket, and every not take is take for the other bucket. Yeah, so yeah, that's the problem D. I think that's clear. Now let's move to the E problem. I'm not sure anybody is watching for this part anymore, and sadly this is the most interesting problem of the contest so far. Like, might be F is more interesting, but I haven't solved that one. Oh, F has very few solutions. Wow, just 5. Okay, so zebra-like numbers. I took a lot of time on this one to figure out a very simple thing. Uh, it's that, I mean, I think it was more of a hit and trial sort of thing, but yeah, if you have numbers like 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, and so on. So one thing you can notice is that these numbers are basically ax equal to a of x minus 1 multiplied by 4 plus 1, right? So that's how it's working. You can even see the numbers 1, 5, 21. They follow this. 1 times 4 plus 1 equal to 5, then 5 times 4 plus 1 equal to 21, and so on. Okay. Oh, nice. Yeah, I think you were close, this Z to Z thing. Yeah. Anyway, uh, so basically these numbers are very very big, and what you can see is that wow, so there are a lot of things here. You have L, R, and K. So basically, you have to find in the range L to R how many values you can, have the zebra value equal to K, and what zebra value is that um, it's the minimum integer such that your value can be expressed as a sum of that many zebra-like numbers. Um, yeah. Anyway, so you have to build some intuition somehow. I'm not very sure how I was able to do it, but since the number are like these, uh, getting the minimum number of zebra numbers to form a number is actually greedy. So if you had like let's say 100, and if I had to find what's the zebra value of 100, I can just do it greedily. First I take 85, then 3 times 5, right? So it's just greedy. You have to sort of notice that this is greedy, and there are so I went to extreme lengths. Was anybody able to prove that this was greedy? So I went to extreme lengths to actually prove that this is greedy. Not sure if it works as a proof, but uh, I think what I came up with was something like if like if I have a number with like some high bits, and if I have to get rid of this bit, I have to use something like this, right? So it being not greedy would mean that instead of doing this, I do this, and you can sort of work in that direction, and you'll see that you'll have to waste 3 operations to make this come here, and with those 3 operations you could have done everything else. So that's why it is greedy. Oh, hi Yogesh. Oh, why did you retract that? But yeah, anyway, so you have to sort of notice that this is greedy, and then after that, there's a very simple technique here that you have to calculate the answer. Basically, let's say you know the answer for 1 to r, right? Let's say if this is function of r, so then your answer will be equal to f of r minus f of l minus 1. This is a very standard technique again, used a lot in digit DP. This is also a digit DP sort of question. But yeah, so this is a very standard technique, and now you just have to find f of r, right? So what we can do is, first of all, we can see, yeah, first thing we can see is that k will never be that large. So k, I think it's easy to come up with some bound for k. It's, I think, maybe close to 120. So k is probably never greater than 120. I worked with 150 for this problem, but yeah, you can probably prove that k can be max 4 into 60. Yeah, I think you can get a tighter bound than that. uh, it's like, I think it's close to 2 times, maybe 4 times 30. Yeah, I think 120 is the bound. I'll show how that works. So like if you have any number 1 and then 10 xyz dot dot dot, or it could be 11 xyz dot dot dot, right? So let's say if we want to, get rid of one of these bits, like if I want to get rid of this. So there are two cases again. Then like this could be an even bit, or this could be an odd bit. And then again I have 10 xyz dot dot dot, 10 xyz dot dot dot, right? So yeah. So in this case, I can subtract it with 10101 and so on. And in a single operation, I get rid of one bit. So one bit is gone in a single operation. Whatever I'm writing is not visible. What would that be the case? Let me check. Was it ever visible what I was writing throughout the stream? Okay. It seems stuck. Yeah, it seems stuck. I'll have to check why that's happening. Oh wow. Okay. I don't know since when it was stuck. Anyway. So anyway, these are the 4 cases basically, right? Um, the most significant bit could be at an even position or an odd position, and then the next bit can either be 0 or 1. And this is 1. Okay. Right, so these are the 4 cases, and then you can see in this case, you can sort of subtract it with this and get rid of one bit. So one operation to get rid of one bit, right? In this case, you can subtract this at max twice, at max 2 operations to get rid of one bit, right? Then in this case, yeah, so again in this case you can subtract it with this and get rid of one bit in one operation, right? Now only this case is remaining. Sorry, only this case is remaining. So in this case, it might be possible that you can subtract it with this and get rid of one bit, but it might not be possible as well. So in that case, what you can do is you can take this one and subtract it twice. So then this becomes something like this, right? So if you subtract this twice, you still get rid of this one bit, right? So we can just say this times 2. So again, at max 2 operation. So you can see that to get rid of any highest significant bit, so to get rid of any most significant bit, it takes at max 2 operations. and generally one operation. So I think on an average it takes maybe 1.5 operations. Still, like in the worst case it will take two operations. So 60 times 2 is like 120 or close to 120, right? So maybe 128 or something, I'm not sure. But yeah, so the bound is close to 120. To be safe, I worked with 150. Is that clear? But yeah, so anyway, can I make a new? Yeah, so anyway, so basically, yeah, so k, for any k greater than maybe 150 or something, you can just return 0, because greedily you can see that like you can easily come up with some bounds. It probably even less than 100 or something. We'll have to wait for the official editorial for the correct bound. But yeah, 120, 150, 200 definitely works. Yeah, so now let's work with some DP for this. um, so yeah, let me see the solution once. So this is sort of like a digit DP. Let's see what we've done here. Yeah, so I wrote a comment here to kind of help, uh, but I have to explain what this is. So anyway, so let's take, we have to work with the FR, basically in the range 1 to R, sort of find how many have zebra value k, right? So in the range 1 to R, I have to find how many numbers have the zebra value equal to k. So what I can do is I can first greedily find how to build R. So R could be like, let's take an example. Um, let's say R equal to 103, right? So it will be 85 plus 3 into 5 plus 3 into 1, right? So you can think of it like a number system. So this is actually 1 uh, 133. So you can think of it like a number system, and this number system, in this number system you have the letters, basically the digits can be from 0 till 4, right? So it can never be 5, because you know 4x plus 1 equals 4xi plus 1 equals xi plus 1. So you can never go, like you will never take any element more than 4 times, right? So the digits in this number system is are from 0 till 4, and yeah, so this can be represented by like 133. So yeah, similarly I've written, it could be like, I don't know how this 1024 came from, but for example if it was 1024, similarly like it's 133, so and k was equal to 3. Yeah, exactly. You thought of bound 4 into 60. Why didn't you think 5 into 60? So 0, 1, 2, 0, 1, 2, 3, 4. These are 5 of those, right? So you should have thought 5 into 60 here. But anyway, so basically this number can be represented as like 133. So let's say we had a number that could have been represented by like 1024. So we can, and if k was 3, we have to get numbers that are smaller than this, and the total sum of digits is equal to 3. So like it could be 1002 or 1011 or 1020 and so on. I've written all of these here, right? So you can see that the sum of digits here is equal to 3 for all of these, and all of these are smaller than this one, right? So basically this is the sort of digit DP you have to do. There's only one corner case, and that corner case is basically you have to make sure that if you have put a 4 anywhere, you can't, it has to be followed by all zeros, right? So what I'm saying is that you can't have a number of the form 1041 or 10401 also, for that matter, because yeah, so you can think of it like, if I have 4 times 21 plus 1, right? So this number becomes 85, right? So uh, obviously you'll never use you know if you try to break it down again, it will be 85 back, right? Is that clear? I'm not sure how to explain this part, but yeah, basically any number, if you have 4 times 21, um, you cannot represent it using fives and ones, right? Or not even with 85. But if you have 4 times 21 plus anything else, plus 5, if you have 4 times 21 plus 5, then that becomes I think 89, and then 89 will be broken down into 85 plus 4 times 1, right? So basically if you ever have a 4, you must put all zeros on the right. So that's how I've kind of implemented this, that basically when I'm putting the digits in the digit DP, if I have ever put a 4, then I do not allow anything greater than 0 to be filled here. Other than that, you just go to the next index, the total sum you subtract it with whatever you filled here, and this is just that whether you have put a 4 anywhere till now or not. And yeah, obviously if the k is greater than 150 or smaller than 0, then it's not possible. If you have reached the end of the array, then the basically sum of digits that's still required has to be 0, and this is DP. So yeah, so this was the corner case that you kind of have to keep in mind, that 4 times after 4 times any of this zebra number, you can't add anything extra. Yeah, so you can also think of it like this. So zebra numbers work like this. So it is 4 times your previous number plus 1. So in this vector I've stored all the zebra numbers. So zebra numbers work like 4 times the previous zebra number plus 1 to get the next zebra number. So if you have also, we can't. So basically 4, like if you try to represent your number in this fashion, like 1 0 3 3 4 or anything, so 4 can, like after 4 there can only be zeros. So 10400 is allowed, but anything like 1040001 is not allowed, right? Because you can see that any zebra number multiplied by 4 plus 1 will give you the next zebra number. So that's a problem. But if you multiply it with only 3, no matter how much you add from the right side, you'll never get the next zebra number. So basically that's all you have to make sure. This is just simple digit DP. I is the index at which you are, k is the required sum of digits, vector v is sort of containing the digits, bool small is it's a very standard thing in digit DP. You just check whether your number is currently smaller than your array of digits or not. You can sort of see it here as well. If it is small or the current digit is smaller than the required digit, then I send true, otherwise I send false. And yeah, so prep 4 is the only nuance here. Basically, if you have put 4 anywhere in the prefix, you can't put anything here. You can't put even 1 or 2, anything. You must put all zeros, right? So that's the sort of thing that you kind of, yes, okay. Separating LR is, I think, a kind of um, it's a it's a standard technique. It's very standard. Like in most digit DP problems, you can sort of do this. Like whenever somebody asks you how many in the range L2 are, you can always do it how many in the range 1 2 are, and then subtract it, and then do basically get R minus get L minus 1. So this is a very standard technique. Yeah, so if you don't think of this, it will become a little harder for you. So you'll have to keep two variables instead of bool small. You have to keep small and big both, and you have to make sure whether you have to check whether your number that you've built so far in the digit DP, is it bigger than your um, basically array of digits, is it bigger or smaller or in between. So you have to keep multiple variables there, but it becomes easy if you can do this technique, get R minus get L minus 1. So that's that, and then rest is just implementation. This is just simple implementation. How many times, like in this vector v, I'm just storing the um, this digit representation. I like to call it zebra base representation. Yeah, so that's that. I think this was very interesting. The tough part was to sort of prove the greedy part of it, and then the second toughest part was to come up with this bound. But yeah, digit DP is very rare on Codeforces. No, you're wrong here. Digit DP is, I think, pretty common. Like I don't know about right now. At least 3 years ago, it was pretty common. 3 years ago, when I was a regular contestant. So yeah, that's that. And anybody watching, if you have any like doubts or anything, we can talk about that. Otherwise, I have to end this stream. I have to sleep also. Yeah, this was fun. Thinking about doing more of these. Oh, number of participants is very good. 20,000. Is CP relevant at your job? Not exactly relevant, but like I have seen this pattern that the people good at CP are very good at this job, like at least the HFT job. Yeah, people good at CP are like very good at this. I've seen this trend. Yeah. Okay, so I think we can end this for today. Um, like, thank you everyone for joining, and yeah, I'll see you next time. I fail all the criteria for HFT except CGPA. Wow. So which college are you from? And how much CGPA? Actually, you can probably text me on LinkedIn or something, because it's very hard to talk with this 5 second lag. Yeah. Bye everyone, and I'll see you next time. 6. Wow. I have clicked on the end stream button. I'm not sure why it's not working.